We've seen how to transform and act on RDDs of any sort, but there are certain optimizations that can be made if you're working with paired data. And by paired data, I mean any data that's in a tuple 2, where the first element of the tuple is considered the key and the second the value. So, how can we use this structure to our advantage? Suppose we have a dataset with the same key as we have here, 2 A keys with different values, a single C-keyed pair, 3 D-keyed pairs, and a single G-keyed pair. Now, when we run a pair-type operation, the data is repartitioned across 3 nodes. The important part to notice here is that while normally random, the repartitioning here uses a hash partitioner so that all rows of the same key are on the same node. The D-keyed pair would not be split between node 1 and node 2 while using these specialized methods. This has the benefit of future key-based operations being able to execute locally without having to shuffle data across the network, which is due to this guarantee that all the data for a particular key will reside on the same machine, at least while the hash partitioner is active. The partitioner will be kept as long as you continue to use these functions, as they only work against the values, thus guaranteeing that the key remains the same. So, a good rule of thumb is to use these functions if you're working only with the value portion of paired RDDs. Now you know the performance reasoning for these methods, so let's get to them. There are some new methods, however, there are also a lot of methods that we've already learned about, just pair-focused, like collect as map, which does the same thing as collect, except due to it knowing the data's in a key value format, it can be returned as a map. And, along those lines, there are also methods to only extract the keys or only extract the values, along with a lookup method that will return a sequence of values that match the provided key. Next are map and flat map values, which are exactly the same as their non-values counterpart. Then we have reduce by key, which is almost the same as its counterpart, except this version is actually a transformation instead of an action. Why? Well, since we're only working against each key's value group separately, and since we know all the keys are on the same machine, then the reduction can be run locally on each worker without having to pull back to the driver. Although it does have a reduce by key locally method, which acts just like a reduce by key followed by a collect as map. The next 2 methods, fold and aggregate by key, follow suit, in that they're the same as their counterpart, except as transformations instead of actions. And all of these aggregation methods are implemented via the combine by key method, which we have not seen. However, it's nearly identical to aggregate by key. Beyond some additional parameters for performance gains, it accepts a function instead of a static initial value. This function is meant to convert the first encountered value into the initial value to be used by the rest of the combination functions. In the majority of the use cases I've seen, this level of genericness isn't needed. Aggregate by key or stricter usually get the job done. Then there's group by key, which is the same as using the group by method with the first portion of the pair tuple as the parameter. Which, I'll repeat that unless this is actually the final formation you want to save your data in, then there are usually more performant methods available. Especially avoid a common mistake of performing a group followed by a reduce. Opt instead to use the more generic aggregate function in order to combine the 2 operations more efficiently. The last few similar methods are all appended with the by key postfix, count by key, countApprox distinct by key, sample by key, and subtract by key. Then there's sort by key, which is again the same as its non-pair counterpart, except in Scala, it's made available via the ordered RDD functions implicit conversion, while remaining part of the Java pair RDD for its Java counterpart. Then, there are some new functions that should be pretty easy to understand if you have any SQL background. They're the different types of joins, which take two key-valued RDDs and combine them based on key equality into a new pair RDD, where the value side of the new pair is a tuple containing the value from the left RDD and the value from the right RDD. Join, often referred to as an inner join, is the case where the resultant RDD is made up of only values where the left and the right keys match. Then there's a full outer join, which returns an RDD with not just the matching keys, but also the left values that don't match the right's key, where the resultant tuple's right side is filled in with a null. It also includes the right values where the left key doesn't match, with the resultant tuple's left side filled in with a null. Then you have a left join, which is the same as a full outer join, except it omits the right side values that don't match. And the opposite of that is a right join, which omits the left side values that don't match. There's one other data joining method that's similar but not quite as SQL-esque, named cogroup or group with. Both are the same method, just differing names. This method takes your pair RDD and, as the name suggests, cogroups it with another pair RDD. What this means is that the resultant RDD is as if you had run a group by key on each of the RDDs and then stuck the values from the two in a tuple. So, the calling RDD groups its one keyed values into its own sequence, and the other RDD groups its one keyed values into its own sequence, and those sequences are added to a resultant tuple. You can have an empty sequence, such as the case here, where there's not any 2 keys in the right RDD, and not any 3 keys in the left RDD. Also, if you need to group with more than one other RDD, these methods have the ability to cogroup with up to 3 other RDDs. Finally, the last methods we'll see available to use for paired RDDs are the saving ones. These methods actually mirror the loading methods that we saw earlier, so should be pretty familiar. First is the save as Hadoop file with its new API counterpart, which takes a path, a class denoting the key type, and value type. Recall that these should implement Hadoop's writable contract. And the last parameter denotes the format with which we want to save our file. Also, if you prefer, the class parameters can be written as generic types in Scala. Then, there's the more generic save as Hadoop dataset, only accepting a Hadoop configuration as its parameter, which is expected to be filled out with all the pertinent information needed to successfully save the dataset. Again, this provides a flexibility to be able to save to any number of outside sources. However, if you just want to save the data as a sequence file, Scala and Python have a convenience method, save as sequence file. In Scala, this is made available via implicit conversions to the sequence file RDD functions object. This is a pretty simple function, only accepting a path as its parameter type, and using type inference to fill in the key value writable types. This is ultimately just a convenience method for a call to save as Hadoop file with the given path, inferred key and value class, and the sequence file output format, which is exactly how you have to call this in Java, which doesn't have this convenience method.